Hello everyone, and welcome to our 5th Destination Space event. Will we find life in the universe? A very good question. My name is Helena and I am an outreach officer at the Department of Physics, and I've been hosting these events. So now it gives me great pleasure to introduce today's speaker. So today we have Burtie Spry. Burtie is a DPhil student here in the department in the Planetary Research Group. So in case you don't know, DPhil is what Oxford calls a PhD, which is the degree that you can study after you've done your undergraduate and possibly a master's degree. And through that, you become a doctor in whatever science or whatever subject you're studying. And he spends his time researching exoplanets. So they are planets far away from our own, located in other solar systems. So he'll be telling you a little bit about that today, as well as discussing the very hot topic of other life potential in the universe. I will hand over to Burtie now, who will tell us more about this subject. So Burtie, over to you. Thank you.
Hi, thank you for that great introduction. Okay, so today I'm going to be talking to you about will we detect life in the universe? So the probability that we will detect life in the universe. So what does this depend on? Ultimately, this is a numbers game, right? So the more stars in the galaxy, the higher the chance we're going to detect life in the universe. Also depends on the number of planets that each of those stars hosts, the number of planets per star. We also care about what fraction of these planets are habitable. There are then biological questions about, given a planet is habitable, what is the chance that that planet goes on to develop life? So thinking about those various chemical and evolutionary questions attached to that. And then also, what fraction of life is intelligent? Because ideally, we don't just want to detect life, we want to be able to detect intelligent life that we can communicate with. Because in all probability, that will be that will end up being one way we could detect life, is if we're actually able to communicate with it. There are other ways that we could go about it as well. But for this talk, I'm mainly going to focus on these two questions. So you could almost you could easily devote an entire talk to the last two of those more biological questions. But now I'm going to focus on how many exoplanets are there in the sky. So we know this number relatively well, the number of stars in the galaxy. So yeah, we know the number of stars in the galaxy relatively well. So we can, if we know the number of planets per star, we know what the number of planets there are. And we're particularly interested in the number of planets within the galaxy. In all probability, if we're going to communicate with such a civilization, just due to the amount of time it would take light to travel, we're pretty much limited to our own galaxy here rather than the entire universe. And also we care about what fraction of planets are habitable, and I'm going to talk about that as well. So for the first part of the story, in order to estimate the number of planets there are within the galaxy, this is a story of exoplanet detection. So I'm going to talk about the various methods that we can use to detect exoplanets. To answer the second question, what fraction of exoplanets are habitable? One thing that we've noticed in studying exoplanets is the diversity of exoplanets is far, far larger than what we see within our own solar system. And the question is given there is this enormous diversity, what fraction of these could be habitable? So I'll give some examples of some of the really weird and bizarre worlds that we've seen, and also try and break this down into sort of the key variables that we might care about when defining what is habitable and what is not habitable. So you've probably seen images like the one on the right in the media. It's important to emphasize that these images are always going to be artists' impressions of exoplanets, because there's we're currently not able to go and visit these directly. All measurements of exoplanets are either made on Earth using ground-based telescopes, or from space, but in orbits sort of close to Earth, within our own solar system. We currently do not have the technology or capability to send probes outside of our solar system. So that begs the question, how can we detect these incredibly faint, small objects? in the sky. One way we can do this is using direct imaging. So this is just taking a picture of the star and planet, such as what we have on the right here. But the problem is that that the star is typically 1 million times brighter than the planet. So if that means that the star is going to completely swamp out the planet. So we need some way of blocking out that starlight. And one way you can do that is you can place a disk in front of your telescope to block out the light from the star. And that leaves you with the light from the planet. So this is what it's illustrating on the right here. So we have the starlight, and we've placed a black disk in front of the telescope, in front of the star, to block out the starlight. And you can see a very faint planet just on the right here, which suddenly becomes visible when you block out all of the starlight. And on the left here, we have a real an animation of some real data that was taken, and you can see that there are four planets, 4 exoplanets in this image. So you have 1 here, 2, 3, 4, and this image was taken over many days. You can see the timestamp at the bottom there, and you can see the planets orbiting around, which is, yeah, it's pretty cool. But you can also see in this image that as you get closer and closer to the star, you still can see that we're not able to block that starlight out perfectly. There is still some noise coming from the star. And this is what really limits this method. When you get close to the star, you still see a lot, some residual light from the star. So we need a different method if we want to look at objects that are really close to the host star. One possible way of doing that is the shadow method. So if you're lucky and the system you're interested in is edge on, so you have your star and you have planets orbiting around like this, occasionally that planet will pass between you and that star. And when that planet passes between us and the star, it will block out some of the light. And what that will look like from our perspective is it will look like the star is just getting a little bit dimmer as that planet casts a shadow. And we can measure these. So this is what's shown on the bottom here. This is the brightness varying over time. And we can see that there are these dips, and these dips are associated with the planet passing in front of the star. And we can measure various things from these dips. Most notably, we can measure the size of the planet. So a bigger planet is going to cause a bigger drop in light. However, not all systems are going to be edge on. Some systems are going to be, for example, face on. And in such a system, that you're never going to have this shadowing event. So we need a different method to explore such a system. So one way we could explore this is using the wobble method. And I'm sure you're all aware that the Earth orbits around the sun because of the pull of gravity from the sun acting on the Earth. But there is also a pull of gravity from the Earth acting on the sun, and that causes the sun to wobble ever so slightly. And this is, of course, true for all of the planets within our own solar system. So all of the planets cause our sun to wobble ever so slightly. And the same is true with exoplanets. So if you have an exoplanet orbiting around a star, that exoplanet is going to cause that star to wobble ever so slightly in the sky. And we can actually measure this incredibly tiny wobble. And we can do this using a rather clever method. So, and this method is called the Doppler shift, which some of you are perhaps familiar with from school. So the Doppler shift is what causes an ambulance to sound higher pitched when it's moving towards you and lower pitched as it moves away from you. And the same physics applies to light as well. So if you have a light source that's moving towards you, it appears to be slightly bluer than if it was moving away from you. And we can measure this change in color of stars to tell if there's a planet orbiting around it. And because the wobble is caused by the gravitational pull of the planet, we can work out things like how heavy the planet is, and we can also work out what the orbit of the planet is as well using this method. So this isn't really a method used for detection, but I include it anyway because it produces some really beautiful images. So we can observe planetary disks using ground-based telescopes, and we can get these images by combining light from many telescopes to get these really remarkably sharp images. And this is what these are really good for observing planetary systems as they form. So when you have a planetary system forming, you have a disk filled with gas and dust. And these dust grains collide together, forming pebbles and then boulders, and these gradually collide and combine to form bigger and bigger bodies until you eventually end up with planet-sized objects. And these planet-sized objects are orbiting around the host star, and as they orbit around, they sweep up all the material within their orbit. And what you can see here is you can see the colors are the dust within the disk, and you can see that this has been swept out. Various orbits have been completely swept out, and what you're seeing here is you're seeing planets form, and so you're directly seeing planet formation outside of our solar system. So this video really nicely illustrates the total number of planets we've detected so far. So far, we've observed over 4,000 exoplanets, and this video shows them in order from the widest orbit to the smallest orbit. And it really shows the diversity in exoplanets. So the widest orbit can take it can take millions of years for the planet's orbit around its sun. So it would take a million Earth years to be 1 year on the. And for the closest dim planet, 1 year could take only tens of hours. So whizzing round its host star remarkably quickly. And the striking conclusion we can draw from observing all of these exoplanets, and the fact that we've detected over 4,000 so far, is we can conclude that we think there are there's over 1 exoplanet per star for every star we can see in the night sky. So we expect there to be at least 1 exoplanet per star. So this is the key answer to the first part of our question. So first of all, we wanted to know how many exoplanets there are in the sky. And the answer is there's around 1 per star. The second half of the story, we can consider the diversity of exoplanets and what fraction of those planets are likely to be habitable. So I've got some examples of some really weird planets here. So this was among the first planets. So these were among the first planets we discovered, and they're also among the weirdest. So, so our sun is a main sequence star. So it's in the main part of its lifetime. But one possible end state for certain types of star is to undergo a supernova explosion, and it can then leave behind a remnant of the star known as a pulsar. And these can be, and these are very bizarre objects. They are, first of all, incredibly dense. So 1 sugar cube of pulsar material can weigh around 1 trillion kilograms, which is about as much as a mountain. And that's just in 1 sugar cube. And these are also incredibly rapidly spinning objects as well. So these can rotate around 1,000 times a second. And so we wouldn't necessarily expect a planet around a pulsar to be particularly habitable, but they're interesting nonetheless. Pulsars also have incredibly strong magnetic fields, so we could expect that these planets could have really strong aurora, so like really strong northern lights on these planets due to the host stars' really strong magnetic fields. And another example of a weird exoplanet is Kepler 16b. So this is a real life Tatooine for those of you who like Star Wars. So a planet that's orbiting 2 stars instead of 1. And it's not, we don't just expect, so this planet happens to be orbiting around both of the stars, but that's not the only combination. So we could have a system where the planet orbits around just one of the stars. And this could be incredibly weird. So imagine what a day would be like if you were living on a planet which is orbiting just around just one of the stars. So at certain times of the year, you'd have your planet here, a star here, and a star here. So as the planet spins around, you'd go from day, and then when you're seeing one star, then as it spins around, you're just seeing day from the other star. So at certain times of the year, your day would last 24 hours. So you go from day to dusk without ever going to night. Whereas at other times of the year, both of the stars will be in the same part of the sky, and you'd have more of a normal day-night cycle. So this would be, it would have incredibly weird years on such a planet. There are also incredibly extreme planets. So WASP 43b is an example of one. So this is a planet that's orbiting very close to its host star. So it's a Jupiter, well, 2 Jupiter masses. So it's, imagine just taking Jupiter and bringing it closer to the sun. Until a year on this planet lasts 19.5 hours. And this planet's incredibly hot. So the day side of the temperature is around 2000 degrees, and it has around a 1000 degree day-night temperature difference. So it would have incredibly strong winds on the surface and superheated to ridiculously high temperatures. So let's try and sort of bring this together in terms of sort of some general variables. What kind of things do we need for a planet to be habitable? So one thing that's important is temperature. So we might want to have liquid water on the surface. So this tells you how close into the host star your planet needs to be. A second thing that's important is the orbit circular. So you could have this sort of egg-shaped orbit here, and on such an egg-shaped orbit, you'd have it would get incredibly cold at certain times of the year, and as it gets really close into the star, it would get really warm. That perhaps wouldn't be very good for life if you had an annual kind of global freezing event and then a superheating event at other times of the year. That probably wouldn't be great for life. Binary systems, but we already mentioned that. So the idea that you could have, you could be orbiting more than one star, and these systems aren't rare. Binary systems are incredibly common. Planetary mass is another thing that's important. So, for example, do we have a gas giant, or do we have more of a rocky planet like Earth? Does the planet have an atmosphere? So again, something we probably need for life. And also, what is that atmosphere made of? Do we need to have something? Do we need oxygen? And also, certain planets might have sort of acid rain and things like that. I mean, this would be very, potentially bad for life. So thinking about what is the chemistry of the atmosphere going to be too inhospitable for life as well? And these last two questions are ones I'm particularly interested in, and I'm working on a space mission that is devoted to answering these two questions. And this mission is called the Ariel mission. Okay, and yeah, this mission is devoted to answering those two questions. It's going to directly measure the atmospheres of exoplanets. And it's going to do this using the shadow method I described earlier. So it's going to look at planets as they pass in front of their host star. And based on various properties of the shadow that it creates, we can tell things about the atmosphere of the exoplanet. And we can work out things about whether it has, for example, clouds, what the atmosphere is made of. We can tell the difference between gas giants and rocky planets. answered lots of really important questions about exoplanet science. So this is the telescope itself. So you can see you've got the service module at the bottom here. So this is responsible for the basically the steering of the telescope, and you've got the payload on the top, so it's responsible for all of the science. And you can see the light entering and passing as it passes through the optical system. And as it does so, it gets split up into the different colors, and eventually gets collected by the detectors, which are these boxes here. And these are just some examples of different types of exoplanets that we could expect to see. So we could have worlds that are ocean worlds, completely covered with water all over their surface. We could have magma worlds, so worlds that are so hot they're heated until the rock is completely liquid. And on the other extreme, ice planets. So planets that are just frozen over. And alongside that, there are of course gas giants as well. There's also the possibility that we can measure we can detect the moons of the gas giants, as well as measuring the properties of the planet itself. Okay, with that, I will finish my talk, and yeah, I welcome any questions.
Brilliant. Thank you so much for that, Burtie. So let's get to our exoplanet questions. So we've had a lot of people asking about these sort of habitable conditions, and I think we answered most of that, at least to some extent, in the talk. But we've had some really good questions kind of asking about the sort of life that we might find these conditions habitable. So one question here, could one planet be habitable for one species, but not for another? So do you think that could be the case?
Definitely, yeah. So this is one of the real challenges of trying to work out what is habitable for an exoplanet, because we only really have one example. Well, we can look at the life on Earth, and we can say that Earth is habitable for this type of life. But do we know that all of these conditions are necessarily required for life? Could life evolve in a completely different, unrelated, a completely different set of environments? And that's quite possible. So we've kind of got to keep our imagination very open to the types of life that could exist. And yeah, so you could certainly imagine that on a completely different planet, life could evolve to survive in some really inhospitable conditions.
Yeah. And I noticed someone in the chat asked about oxygen. So would oxygen need to necessarily be a requirement for it to be habitable, or could species evolve that don't need oxygen, do you think?
This is, I'd say, a question that a biologist would be able to give you a definitive answer on, but I think I wouldn't say that it would be necessary. I imagine you could devise ways of creating life that relied on other different chemical pathways. Yeah, I need a biologist to confirm.
Yeah, I think a lot of these sort of questions about the mechanics of the possible life and the habitability are best answered by a biologist. So keep them in mind if we're not able to answer today. So another question, you might know the answer to this, again, it's on a similar vein, but if we were to find alien life on other planets, would it be a complex organism such as is displayed in movies, or are we more likely to find microbes, for example, bacteria?
Well, that's an interesting question, because there are two sort of halves to that, right? So first of all, I guess, is which one is most frequent. So I would imagine that given it's probably easier to form microbial life, I would expect that microbial life be more common in the universe. But perhaps we would more likely to be able to detect an advanced civilization. So one way of detecting the presence of life would be, for example, you could look for chemicals in the atmosphere that would only be present if a civilization put them there. So one example is perhaps not the most rigorous example, but you could imagine that if you looked at Earth and you measured the amount of carbon dioxide in the atmosphere, you could say that that is proof of life, because there is no way that such a high amount of carbon dioxide could have got in the atmosphere without human involvement. And there are lots of other chemical species that we could use to measure that.
Fantastic. Okay, so I think moving away from the sort of alien life questions for a little bit. So we've got one here that's really interesting. So if a planet is tidally locked, can that potentially increase the chances of it being able to harbour life? And they've suggested due to the narrow strip where the temperature might just be perfect. So could you maybe explain a little bit about what that means, and also answer that for us?
So the idea that if it's tidally locked, the impact on life.
Yes.
Yeah. So so the idea. So first of all, tidal locking is when we have a planet that's it typically is orbiting very close to its host star, and such that the gravitational influence is so strong that the day side is a permanent day side. The criterion is that so the orbital period is the same as a year, and so the day side is always facing the star. And this would, I imagine life could form on such a planet. The key difference for a tidally locked planet compared to a non-tidally locked planet would be certain areas will be permanently hot and certain areas will be permanently cold. But I imagine there will be sweet spots, for example, on the equator, that you could have. On the sort of bit between day and night, you could imagine there are sort of Goldilocks regions there where it could be just the right temperature for you.
Brilliant. So that could be a whole new kettle of fish that we're dealing with if we've got a tidally locked exoplanet. Brilliant. So we've had a couple of people also asking, going back to the methods that we use to detect exoplanets, why can we not only use the wobble method? Why do we need to use other methods as well?
So each of those methods is really good in a certain specific, for certain specific types of planets. So the wobble method is it's a gravitational method, so it's more sensitive to heavy planets, and it's also more sensitive to planets that are close into the star. But if the planet transits, you're more likely to detect the planet. So if the planet passes in front of the star, that's what I mean by transit. You're more likely to detect it with by using the shadow method, so looking at the drop in light, because you can get lower noise data that way. So each of those methods is good for certain types of planets, and when we can combine them, certain planets we can do multiple methods on, and when we can do that, we have a whole wealth of information about one planet, and that's great.
Brilliant. So they each have their pros and cons for different types of planets. Nice. Okay, so we've got someone asking here. I don't know if you know the answer to this, but they've asked, was it an asteroid that hit Mars and made it lose its water and possible life there? So is that true? And could that maybe, I guess, be an issue for other exoplanets?
I'm not sure why Mars lost its atmosphere. I imagine it also has something to do with its gravity, to the gravitational strength, but because it's I'm not too sure. Okay,
cool. I think you'd have to ask someone who specifically studies Mars for that question. Brilliant. So you said that you estimate that every star would have an exoplanet orbiting around it. But I noticed someone asked on here, how many stars are there? So how many exoplanets could that possibly be? Could you give that a number?
So within our own galaxy, we think there are 10 to the 11 stars. So that's a 1 followed by 11 zeros after it. So an enormous number of stars within our own galaxy.
Amazing. So many, many potential exoplanets. Okay, another good question here. You might know the answer to. What determines the shape of the planet?
Well, the planets are all going to be roughly spherical, just because of gravity. the lowest energy configurations. If gravity just wants to pull it into a sphere, that can change. You can end up with things that are not perfectly spherical, so you can end up with some planets that are have a slightly wider at the equator. If they're very rapidly spinning, you could end up with wider equators, for example. So it doesn't have to be a perfect sphere, but they'll be roughly spherical.
Okay, interesting. And another good question here. How do we see the atmospheres of exoplanets?
Right, this is really delving into some of the details here. Yes, so the way we do that, so we do it using the shadow method, and we measure the dip in light as the planet passes in front of the star. But we don't just measure this at one color. We measure this at lots of different colors, and that produces like a fingerprint. And we can compare that fingerprint to the known fingerprint of different chemicals. So we can measure these the fingerprints of these different chemicals in a lab, and we can compare this to the fingerprint we measure by observing at lots of different colors of the exoplanet.
So I've seen a nice one here. If we do find life on one of these exoplanets, could we possibly send people to those planets?
I don't know if we could do it in our lifetime, but maybe one day. We can always dream.
Okay. And do you have an idea for the sort of percentage of exoplanets that you found so far that would be considered habitable?
Well, the definition of habitable is still a tricky one for for some of the reasons I described earlier. So we don't the question of how wide do we cast our net in terms of defining habitable? So one possible definition of habitable is, does the planet have liquid water? And you could probably, you could make some comparisons about that at the moment. We could say that at the moment, all we can really say, we can think about sort of the masses and temperatures of exoplanets. This is what we really know at the moment, and the orbits. In order to really be able to do sort of statistics on atmospheric composition, we really need to wait until the Ariel mission, the one that I'm working on, to really think about things like what the atmosphere is made of. And these are other key numbers we really need in order to estimate that accurately. So maybe within 10 years, we'll have a better answer to that question.
Brilliant. So this is actually the sort of cutting edge of this type of research at the moment. Fantastic. Exactly. So we just had someone here asking, why is the mission called Ariel? So where did that name come from?
So it's one of these very long acronyms. So it's Atmospheric Remote Sounding Infrared Exoplanet Large Survey, I think it stands for.
Sounds about right. We like our acronyms in science. I think I've mentioned that before, and it's one of these things that we need to remember, that we need to explain to people who aren't working directly on the same things we are. Okay, I think just one final question. Speaking of scientists naming things, is there a more scientific name for the wobble of a star that is caused by the gravitational pull of planets orbiting around it? Or is that its technical term?
Yeah, so this is more commonly referred to as the radial velocity effect. So that's coming from the fact that we measure the speed of the star, the velocity of the star, and we're also the name radial comes from the fact that we're measuring the part of the motion towards and away from us. We can't measure it. If it was moving in this direction, we wouldn't be able to see it. But if it's moving in this direction, we can detect that. So that's why it gets the name radial velocity. And also the shadow method is also has a different name that goes by the name the transit method as well.
So unfortunately, wobble isn't the technical term here. So with those images that you took that were made into GIFs, someone's asked, does it take years to take those images? I think we could just about see that on the timestamp. So I think it took a few years to get all those images. Am I right?
Yeah. So we're observing we're observing them as they orbit their host star. So that's And so, so if you're seeing orbital shifts, you're seeing fractions of a year on that planet. So that's going to be comparable to years on our planet. And the ones we observe by direct imaging are always the ones that are really far out. So years for these planets always takes a lot longer than a year on Earth. So in order to see that motion, we have to observe for a really long time.
Brilliant. And I found the question again. So just very quickly, how do we name exoplanets?
Well, they always get given these really inelegant names like WASP 43b and stuff, and it's just it's a systematic naming convention. Unfortunately, I think it would be nice if we gave them some more romantic names, but at the moment it's just the systematic convention.
So if you managed to discover an exoplanet, you couldn't name it after yourself then?
Unfortunately not.
That's a shame. Okay, and on that note, I think we will end it there. So thank you so much for coming, everybody. It's been lovely to have so many people here and interacting with the questions. And thank you, Burtie, for giving such a fascinating talk about exoplanets and the possibility of life in the universe, and for answering so many questions. So thanks, everyone, and we'll say goodbye. So bye.